Okay, welcome back to Special Topics of Semiconductor Technologies. In this section, we'll discuss the so-called diode. Okay, diode is basically a device we call that a PN junction. The PN junction means you got a P-type semiconductor and another N-type semiconductor back-to-back connected together, and this is called a PN junction, and this is called diode. For diode, it only allows electric current go through only one directions when it is positively biased. That means the current only allowed to go from here to the right, not able to from left, right to the left. When you have PN junction, the current always coming from P side to the N side, not N side to the P side. It's called diode, and this also has a rectifying behavior. So because the current only going through in one direction, so it will not behave like alternating current, the current coming through back and forth. Okay, only half of the signal is passing through a rectifying process. So when you have a circuit with a diode inside the circuit, then all the alternating current only going through half of the signals. Unlike the previously discussed the resistors and capacitor, the diode is a nonlinear device, so the response of the current to voltage is no longer a linear relationship. A diode allows the electrical current to go through in only one direction when the voltage is forward biased. It will not allow current to go through if the applied potential is reverse biased. So when you have bias for the P and N, when you have P side connect to the positive and N side connect to negative polarities, and this is so-called forward bias. And current going through. And you have P-type semiconductor connect to the negative polarity and N-type connect to positive polarity. This is called reverse bias, and no current going through. Okay, and this is the symbol of the diode in the electronic design. This is P side and this is N side. So when you apply voltage, when you have V1 voltage higher than V2, and then this will be the forward bias, so the current will going through. But if V2 is larger than V1, no current will going through in this device. This kind of mechanism is similar to the tile valve, and this is the tile valve, a schematic drawing. When you pump up the air into the tile and the pump pressure P1 is higher than the pressure P2 inside the tire. The higher pressure open the valve, so the air flow into the tire. Okay, so the air going through the tire. Without a pump, tire pressure P2 is higher than the atmospheric pressure P1 in this situation. Therefore, the pressure difference close, the pressure is higher than P1. The air coming from right to the left and close up the valve here. So all the air inside the tire will remain. And this is similar to the diode, as we mentioned, when it is forward biased, V1 greater than V2, the current going through. When the V2 larger than V1, no current coming through. Similar here, P1 atmospheric pressure is greater than the tire pressure in P2, so the gas coming to the tire. If the tire pressure is greater than the P1, so the valve is being closed and the tire will seal up and the air will within the tire. This is concept of diode. When you have P-type semiconductor and N-type semiconductor back to the connect together, something happened. Over here, you are supposed to have a lot of hole in P-type due to the introduction of group 3 element, and in N-type area the group 5 element was introduced, so you got a lot of electron. You got a lot of electron here. When the two semiconductors contact with each other, because of the concentration gradient, okay, you have concentration gradient. Because of concentration gradient, the more electron at the right hand side will diffuse to left hand side by diffusion. Once the electron moving from the right to the left, the atom at the p side receive electron and form a negative charge ion. So you got ion here, negative charge ion. But because of electron is losing to the left, so all of the atom here become positive charge ion. Therefore, at the interface, near the interface, you have negative charge particle and positive charge particle over here, and then you were creating an electrical field from the positive ion side to negative ion side, and this electrical field is try to push away the hole coming from left p side to n side. Because of the field, electrical field is basically try to push hole to the left to the electrical field direction and electron to the opposite direction. This is what the electrical field tries to do. But when the charged particle form in the vicinity of the interface, the junction, so a electrical field form with a direction from right to the left. Okay, and this will against the natural diffusion of electron or Hall movement, because the natural diffusion process will push the electron to the left, but actually for the electrical field it tries to push electron to the right. So that means for the electrical field you form here, it becomes an obstacle for the electron or Hall to overcome. So you form a so-called built-in voltage here. This is built-in voltage. Due to the p-n junction, and this built-in voltage will try to stop the natural diffusion of electron to the left or Hall to the right. Okay, the electrical field here is positive and negative, so electrical field is in this direction. Okay, so electrical field is trying to push the Hall to the left, so it's against the natural diffusion of Hall to the right, and electrical field is trying to push electron to the right, again against the natural diffusion from n side of electron to moving to the left. Okay, so eventually when it balanced, it formed a built-in voltage, and this built-in voltage actually you can calculate by theoretical consideration. Okay, this K is Boltzmann constant, T is absolute temperature, this charge number, log n sub A is, this is acceptor. Okay, this is acceptor, and this donor number, acceptor number, donor number, Ni is the ion number. Because based upon the theoretical consideration, you can come up with the so-called intrinsic potential, the built-in voltage. The built-in voltage for silicon, and the built-in voltage is somewhere around 0.7 volts. Okay, for silicon. That means when you have a p-n junction form, an obstacle of 0.7 volt is occurred. When you try to have a more electron or Hall running through the interface, you need to apply more than 0.7 volt according to the electrical field. So let's look at the current and voltage curve for a diode. When you have positive bias, that means forward bias, this P and this N, we're connecting to external power. It's positive and negative. In this case, this is called forward bias. when you have voltage, external energy higher than 0.7 volt, and then in forward bias, current going through according to your voltage. But if you are in reverse bias state, this negative, this positive, you always form a reverse bias. No current coming through. Okay, no current coming through. So basically no current coming through. But actually you can see there's a little bit gap over here. Somehow you can find a very little number of current coming through under the reverse bias status. Let's see what is the reason for this. Remember when we say during the P-type or N-type semiconductor, let's say P-type, the N-type semiconductor, you have donor level. Over here, somewhere about 0.05 electron volt beneath the conduction band. This is conducting band. And this is valence band. At the conducting band, you have a lot of electrons from here. According to your application, you have introduced a lot of number of electrons, group 5, say arsenic or phosphorus. Let's say if you have 10,000 electrons at the donor level. When temperature increase or you apply external energy, all these 10,000 electrons will jump from donor level to conducting band. So you have electron here. How many electrons over here? That will be 10,000, because you put 10,000 atoms here. But since the energy gap over here is 1.1 electron volt, the Eg much higher than 0.05 electron volt. So basically only those donor level electrons jump to the conducting band, forming a conducting charge particle, the electron at conducting band. But other than 0 degree K, electron always absorb energy. It will try to jump from valence band to conducting band. If this occurred, a hole will leave behind an electron jump to the conducting band. If some of the electron actually able to jump if you have 5 hole, 5 electron jump to the conducting band, in this case, this is so-called intrinsic semiconductor properties. Intrinsic semiconductor properties. What happens right now is you will end up with 1010 electrons for the donor atoms plus 5 electrons from intrinsic property. So you end up with 1005 charged particle of electron. But you've got another 5 hole over here. Another 5 hole. So you always have primary charged particle and secondary charged particles. In this N-type semiconductor, the primary charged particle will be electron. You've got 1000, 10,000, and 5. And secondary charged particle, that'll be hole, only 5. See, even for N-type semiconductor, you have 2 types of charged particle. One electron, the other one is hole. But for N-type semiconductor, primary charge carrier is electron, 10,005, and secondary charge particle hole only has a little number of 5 holes contributing to the electricity. So it is only very minute number of secondary charge particle. Basically, you can neglect. So remember this: primary charge particle is the charge particle contributing the major current, but the secondary charge particle also contributing to the current, but with a very neglect level of current. So that's coming back to here. You can see over here a very small number of electron of current going through at the reverse bias, because the secondary charge particle always exists. Secondary charge particle always exists. It came from the intrinsic property of semiconducting material. Electron jumping from valence band to conducting band. And forming, and always forming an electron and hole. It doesn't matter it's N-type or P-type materials. For N-type materials, this will be secondary charge particle. For P-type materials, this will be secondary charge particle. So remember this: the secondary charge particle or minor charge particle, okay, secondary or minor charge particle always exist, but with very little number of the current count. Okay, so over here it's because of secondary charge particle, and this is primary, and this is for secondary. or we say this is major charge carrier and this minor charge carrier. Okay, for forward bias, primary charge carrier dominate. For the reverse bias, only secondary charge particle will going through. This is so-called IV curve for a diode. Sometimes you will use this specific function of the IV curve. One of the IC called Zener diode. It's a diode design that use this curve as some way, and we're coming down, large breakdown current coming through, and this at this specific voltage, okay, and this is called the Zener diode at the fixed voltage device. Zener diode. When the reverse bias to a design level, a large current going through. So always, for example, this is minus 20 volt. At 20 volt difference, current always going through. So the device here may be a motor, will turn on when the voltage difference reach 20 volt. This is called Zener diode, one of the device used in the electronic design when you try to have a fixed voltage device operating at specific voltage level. This is called Zener diode. Okay, this will be the topic we talk about the diode. Okay, let's make a conclusion here. For diode, it's a P-N junction. When the P connect to a positive charge area and connect to the negative charge area, this is called forward bias. And current going through. Okay, so the current going through. If you have the PN junction with the P connect to the negative and N connect to the positive side of the external power supply, and this is called reverse bias. No current coming through, so it has a rectifying effect. It can be a rectifying, okay, it can be a rectifying effect. Okay, and this is called diode. Okay, this will conclude this section of diode introduction.